We're going to look at some of the parameters you use when evaluating whether a pump is a good pump or doing its job well. One of the things we look at is the power delivered to the fluid. So this is the amount of power that actually gets into the fluid if it's a pump, symbolized by PW. It's rho GH, which is the net head that we just talked about, times the volumetric flow rate here. And so that's the definition of that. But we also know that often, we just said that H is approximately equal to P out minus P in over rho G. So if we plug that in for H here, we get that the power delivered to the fluid is just equal to Q dot delta P, where delta P is equal to P out minus P in. So that's something we saw before, the minimum amount of power that could be delivered to the pump in order to achieve the result in the fluid. So this is the amount of power that's actually delivered to the fluid. Obviously, that's the minimum power, electrical power, for instance, that you could deliver to the pump. That would assume it's a perfect pump, of course, that it had no losses of any kind, no electrical losses, no friction losses. No such pump exists. But at least it's a minimum, you can get what the minimum is, and this is the same quantity that we saw before. So these two values are actually the same thing for that case where Z in is about Z out, and there's no significant change in velocity in the fluid. This is called the water horsepower. So water horsepower, that's what the name of this PW is, water horsepower. All right. There's another horsepower that people talk about, at least for rotary pumps. So for rotary pumps, that is any pump where you're rotating a shaft. They also have brake horsepower. So the brake horsepower, spelled like this, and its symbol is, oddly enough, BHP, brake horsepower. And you calculate it as omega T. Now here omega is your radial velocity of the shaft. Whatever that shaft is that you're rotating to rotate your rotary pump. So it could be the shaft on the propeller, shaft on the turbine, shaft on the fan. So that's your radial velocity of the shaft. And T, of course, is going to be torque. The torque that's applied by that shaft or to that shaft. So that's going to be the way you calculate your brake horsepower. If you know how fast your shaft is turning and you know how much torque is being applied, then you can calculate that. In a real pump, your PW is always going to be less than your BHP. So PW will always be less than your brake horsepower because the brake horsepower is the amount of energy being actually put into the shaft, and not all of that energy is going to be translated without any losses into the fluid. So PW, the water horsepower, is the amount of energy that went actually into the fluid, and the brake horsepower is the amount of energy that went into turning the rotary shaft on the pump. And there's going to be losses because it's going to be friction again in the fluid that's going to just be lost as heat. And we're not doing temperature in this analysis, so we're going to lose some energy there, and we might lose energy. We might lose friction in the shaft as well. So we're going to have some friction losses there. So this is always going to be true that the water horsepower is going to be less than the brake horsepower in any real pump. The pump efficiency is defined as eta, the usual symbol for efficiency in thermodynamics, and you have your water horsepower divided by your brake horsepower. So that makes perfect sense. How much energy you put into turning that shaft versus how much you actually got into the fluid. That makes perfect sense. The pump efficiency has three components. So if you really get into pump design, you actually look up different efficiencies for these different components. I'm not going to get into that level of detail. You can see them in any textbook that gets into pumps. Pumps, of course, are a very, very well-studied thing at this point. There are many books specifically dedicated just to pumps. But the three types of efficiency that pump engineers would talk about would be volumetric efficiency. So volumetric efficiency is A to V. They all have good names like that. Hydraulic efficiency . A to H, and mechanical efficiency. A to M. Pretty simple. So what are these things? Well, basically volumetric efficiency is if you're talking about a rotary pump where you had that vane spinning and you're trying to make the fluid move by rotating fan blades, some of the fluid doesn't really get pushed. It just recirculates, doesn't really leave the pump. Some of it may leak around the housing and not really go out the outlet. I'm not talking about leak actually not your pump's broken and it's leaking all over the place, so that would decrease its volumetric efficiency. But my understanding is also just like some of the fluid just may not move. And so it may just be kind of stuck in the pump. It's not in the flow field. And so the amount of fluid that actually goes through the pump versus the amount of fluid that's getting acted on by the pump may not really be the same. So you may be acting on the blades may be acting on some fluid that doesn't actually move through the pump. And that would be a decrease in volumetric efficiency. Obviously, if your pump was actually leaking water or leaking fluid, that would also decrease it. Hydraulic efficiency is basically the friction in the fluid. So this is the fact that, as we said, the fluid actually is probably turbulent, swirling, all kinds of viscous effects, and that's all going to decrease the efficiency of your pump because just the way the fluid is interacting with itself or with the walls is causing a loss of friction, friction losses in the fluid. And then you have mechanical efficiency, which is what you're probably guessing, I hope, which is the pump itself may have friction. So it's going to have losses that maybe that it's not, it's got scraping or rust or it's just not, nothing's perfectly frictionless. So you're going to have mechanical losses as well whenever you have moving parts. So a moving pump with moving parts is going to have losses that are simply mechanical. The total efficiency for the pump is simply the product of these three. So if you get into this as your profession, your job will be to figure out why your pump isn't more efficient, and then look to see whether your problem is your mechanical efficiency, your hydraulic efficiency, or your volumetric efficiency. All of them contribute to the overall efficiency of the pump, which is measured here. So they decrease, bad efficiencies decrease the amount of power that goes into the fluid relative to the amount of power used to drive that pump.